Welcome back. Today we're going to be talking about the squeeze theorem, and I'm going to be going over five multiple choice and five long answer questions regarding squeeze theorem. All right, so let's remind ourselves, what does squeeze theorem state? Basically, it states that if we have f of x sandwiched between g of x and h of x, and assuming that the limit of g of x and the limit of h of x as x approaches the same value are equal and also equates to a specific numerical value, then the limit of f of x as x approaches that same value must also be that same limit. So let's see how this might apply to this first problem here. It says if 2x minus 1 is less than or equal to f of x is less than or equal to x squared minus 2x plus 3 for all x's that do not equal 2, then the limit as x approaches 2 of f of x is which one of these? Well, here's the thing. I'm going to essentially consider this to be g of x because it's less than or equal to f of x. And I'm going to consider this as h of x since it's greater than or equal to f of x. And I'm going to find the limit for both as x approaches 2. So let's start with the limit of 2x minus 1, which was g of x as x approaches 2. If I plug in 2 here, I get 2 times 2 minus 1, which is 4 minus 1, which is 3. Then if I do the same thing for h of x, I get 2 squared minus 2 times 2 plus 3, which is 4 minus 4 plus 3, which is also 3. And so therefore that second condition is met, right? We already had given to us, the first condition was met, that g of x is less than or equal to f of x less than or equal to h of x. And then furthermore, we also now have that the limit as x approaches 2 for g of x and h of x is 3 in both cases. So what does that tell us? The squeeze theorem tells us directly that f of x must also be the same limit. So f of x's limit as x approaches 2 also has to be 3 as well. All right, let's try the second one. All right, so here's the second multiple choice question. It asks, which inequality would help evaluate the limit as x approaches 0 of x squared times sine 1 over x using the squeeze theorem? All right, so the inequality that we choose must have two properties. Number one, it's got to be correct. And number two, it's also got to actually help us to use the squeeze theorem. So first, I'm going to go through these and we're going to eliminate anything that is false or potentially false. So let's start with A. A looks good because notice that it's saying sine of 1 over x, so sine of some value is going to be between -1 and 1, and that is true, so that doesn't seem to raise any flags so far. B says that sine of 1 over x must be between 0 and 1. And the thing is, that can't be correct because that's not always true. There are values I could put in here for x that would give me numbers less than 0, specifically numbers that are between -1 and 0, right? Because if we think about what the sine graph looks like, it is possible to get those values. And so B is incorrect because it's just not true necessarily. The third option actually has the same problem because imagine if I put in something like 0.1, for example, for x. If I put in 0.1 here, that would give me sine 10 is between um, is between 0.1 squared and the negative version of 0.1 squared. So that would put it between 0.01 and negative 0.01. And is that true? Well, no, because sine of 10 is negative 0.5 approximately. I think it's a little bit less than that actually, but clearly it's not between these two. So once again, there's values I could plug in for x that don't make this true all the time, right? And so since this is not always the case necessarily, that means that it can't be something that would help us evaluate squeeze theorem if it's not even true. And then the last one, yes, that is true, right? It is true that it would have to be between negative infinity and infinity technically. Now, the question is, which one of these would actually help us solve squeeze theorem? Well, the last one doesn't really help us very much. It's very vague. It's basically saying that sine of 1 over x can be any number at all, right? Which isn't as specific as the first one, which is just as true, but is actually giving us more restricted bounds, but still being, but still true essentially as well. And so the answer is going to be A. Now, furthermore, to prove further that this is A, I'm going to kind of go through the steps that we would actually take in order to use the squeeze theorem with this. So first thing I'm going to do is I'm going to multiply both sides by x squared. So if I take this and I multiply both sides by x squared, I would get negative x squared is less than or equal to x squared times sine of 1 over x less than or equal to x squared. Then I'm going to take the limit of all of them as x approaches 0. So limit of negative x squared as x approaches 0. And then over here, limit as x approaches 0 of x squared times sine 1 over x, which of course would seem like it's undefined if we just subbed it in, right? If we subbed in 0, we would get a 0 in the denominator, but that's fine, right? We're not looking for this function when x is equal to 0. We're looking for the limit as x approaches 0, not what it is when it's equal to 0. So that's totally fine. And then the limit as x approaches 0 of x squared. So essentially I'm taking the limit as x approaches 0 across the board here. And then for the first one on the left, limit as negative x squared as x approaches 0. If I just plug in 0, I get 0 squared, which is 0. Then the middle one we're just going to keep as is for now. And then at the end, we have limit as x approaches 0 of x squared. That's also 0. And so it looks like g of x and h of x are both, the limits are both 0. So the limit here would also be 0 as well. So we were able to evaluate the limit using this. Whereas had we started here and just taken the limit with for infinity, that wouldn't have actually helped us. Like that wouldn't have actually helped us solve and get this to be 0. And so those are the two things we need to look for is it actually accurate, but also is it going to actually genuinely help us to do what to actually find the limit. In this case, yes, we found that the limit is 0, so fantastic. We know what the limit is now. Whereas the other one, although this is true as well, it wouldn't have actually helped us, and B and C were just false, and so they were not correct either. All right, let's move on to example 3. So example 3 says if g of x is less than or equal to f of x less than or equal to h of x, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x is equal to L, then what? So for this one, actually, really they're just asking for the definition of squeeze theorem. That's all this question is asking for, luckily. We know from squeeze theorem that if this is the case, if these two hypotheses are the case, then that means that the limit as x approaches c of f of x must also equal to L. Okay, so it's A. It must equal to L. It's not that maybe it does or that it doesn't exist or that f of c is L, right? This could be true, but this is not necessarily always true. And often when we're doing squeeze theorem, we're doing it because f of c isn't always that limit, right? Because we otherwise, why would we use squeeze theorem? We could just plug in the value in most cases, right? And so this is not necessarily true. And then, these would not be the case, that it might be or that it doesn't exist. And so this question is really just checking to make sure that we know what the squeeze theorem states. All right, let's do this fourth multiple choice question. It asks about the limit as x approaches 0 of x cos of 1 over x squared and what that would be. So here's the thing. We know that cosine of 1 over x squared, right? Cosine of anything that hasn't had an amplitude that's been essentially like an amplitude that's been changed, which this has not, right? Anything in this format would have to be between 0 and 1. And so we can say safely that this is between, or sorry, I said 0 and 1, I meant -1 and 1, right? Like if we think about what happens when it comes to the cosine function in general, like what the cosine graph looks like, recall that it fluctuates between 1 and -1, right? That's what it does. Now, there would be a transformation from 1 over x squared, absolutely, but that transformation would not involve making like the amplitude different, and it also wouldn't involve shifting this to make those values, the end values, different. And so because that transformation does not impact that, we would still say this has to be between 1 and -1. Then I want this that's in here in the middle to match what's here. And so I'm going to multiply all sides by x. So here we're going to have -x is less than or equal to x cosine 1 over x squared, less than or equal to x. Then I'm going to take the limit as x approaches 0 on all sides and see what we get. So the limit as x approaches 0 of -x less than or equal to limit as x approaches 0 of cosine of 1 over x squared, and x, I forgot that there, and then limit as x approaches 0 of x. Then for the left and the right, I notice that I can just sub in 0 and I'll get -0 on the left and +0 on the right, and both of those are 0. And so therefore, this is squeezed between 0 and 0. And so therefore it must be 0, right? If this limit is less than or equal to 0 and greater than or equal to 0, well, the only option is it must be exactly 0. And so C is our answer here. All right, and let's try 5, and this is our last multiple choice question. After this, we'll be doing 3 long form questions. And this one asks, which function could be used as a lower bound when applying the squeeze theorem to evaluate limit as x approaches 0 of f of x if f of x is equal to x squared times e to the power of sine 1 over x. So essentially what they're asking is, what would the lower bound be if we wanted to kind of bound this between, between our two places, our g of x and our h of x. So I want to start by looking at the e to the power of sine 1 over x. Recall that sine 1 over x is at least going to be -1, and at most is going to be +1, right? Because recall, sine of some value will stick between -1 and 1, right? And so therefore, the e to this power is in the lowest form, it would be 1 over e, or e to the power -1, and at most it would be e to the power of 1, right? Or just e, I should say. And so we know that this is sandwiched here, right? And then we have to include x squared in the mix. So I'm going to multiply both sides by x squared because I would like to evaluate this function, not just the e to the power of sine of 1 over x. So we're going to end up with x squared over e less than or equal to x squared e to the power sine 1 over x less than or equal to x squared e. All right. So what does this mean though? Basically what this means is that the actual lower bound we should use is x squared over e. And so if that was one of the options, that's certainly what I would choose. However, that isn't one of the options, and notice the wording of the question said which function could be used as a lower bound, not which one is the actual lower bound. So what I'm then going to do is I'm actually going to apply squeeze theorem. I'm going to take the limit of all of these and see what we get, and then whichever function we get technically could have been used as a lower bound. So let's see. Let's apply limit as x approaches 0, x squared over e less than or equal to the limit as x approaches 0 of x squared e to the power of sine 1 over x less than or equal to limit as x approaches 0 of x squared e. So in both the far left and the far right, notice that if we plug in the 0, we get, for the far left, 0 squared divided by e, which is just 0 over e, which is just 0. Recall that e is just a constant. It's just 2.7 something. It's, it's some irrational constant. That's not really super important, exactly the applications of e right now. We just have to know it's some constant. So 0 over some constant is just 0. And then also 0 squared times some constant is also just 0. And so therefore we can say that the limit is going to be equal to 0 based on the squeeze theorem. And there we go. So therefore, g of x we could put it as 0. And if we put it as 0, which is what g of x equals 0 suggests, that will work for us. All right, now let's move on to the first long form question. This next one asks us to use the squeeze theorem to evaluate this limit and show all the steps clearly. Okay, so first of all, we need to be able to bound this by something in order to use the squeeze theorem. Okay, so here's the thing. We know that the sine of 1 over x is going to be between -1 and +1. And then all I need to do is, in order to get this to look the same as this, I need to multiply all sides by x cubed. So over here we'll have -x cubed. Here we'll have x cubed times sine of 1 over x. And here we'll have x cubed if I multiply all sides by x cubed. And actually, I'm going to justify each step because we are explaining all steps clearly here. So basically, this is part of the definition of the sine function. And then this one here, we multiply all sides by x cubed. And then in the third step, I'm going to apply the limit, or take the limit as x approaches 0 for all of these. So then we're going to get limit as x approaches 0, -x cubed, less than or equal to the limit as x approaches 0 of x cubed times sine of 1 over x, which is less than or equal to the limit as x approaches 0 of x cubed. Next, we're going to evaluate the left, or I shouldn't say left and right limit, but evaluate the limits where possible. So on the left side here, we have limit as x approaches 0 of -x cubed. If we plug in 0 there, we get 0 cubed, which is 0. And then on the right, we also get 0 as well, right? We get 0 cubed is 0. And so then we have that the limit as x approaches 0 of x cubed times sine of 1 over x is between 0 and 0. And so then the very last step we would do is apply the squeeze theorem. So apply what the squeeze theorem states, which is basically going to state that therefore the limit as x approaches 0 of x cubed sine 1 over x must be equal to 0 then, right? Because if we have, we're remembering that in squeeze theorem it says that if we have g of x is less than or equal to f of x less than or equal to h of x, and the limits of g of x and h of x are the same, then that means that the limit of f of x, which is sandwiched or squeezed between, also must be the same. And there we go. All right, the next one says, given that 1 minus x squared over 6 is less than or equal to sine x over x, less than or equal to 1 for x near 0, evaluate the limit as x approaches 0 of sine x over x, and justify your answer using the squeeze theorem. So squeeze theorem states, right, that if g of x is less than or equal to f of x, less than or equal to h of x, and limit of g of x is equal to limit of h of x as x approaches any c, which in this case will be 0, then that means that the limit of f of x as x approaches that c value also must be L. So therefore, given that this is our squeeze theorem, how can we use that for this? Well, what I'm going to actually first do is I'm going to take the limit of all the sides here, right? So we originally have 1 minus x squared over 6 is less than or equal to sine x over x less than or equal to 1. So if I take the limit as x approaches 0 on all sides, limit as x approaches 0 of 1 minus x squared over 6 less than or equal to sine x over x less than or equal to, oh, I forgot my limit there, less than or equal to limit as x approaches 0 of sine x over x less than or equal to the limit as x approaches 0 of 1. Well, then on the left, we get 1 minus 0 squared over 6, which is just going to be 1. And then in the middle, we still have the same thing again. And then on the end here, we get 1 as well, right? Because limit as x approaches 0 of 1 is just 1, right? If there's no variable, if there's no x, we can't actually sub 0 in for x, essentially. We just get 1 always. And so therefore, we get that this limit is sandwiched between 1 and 1. And so therefore, the limit as x approaches 0 of sine x over x is equal to 1 based on that squeeze theorem. And so there we go. All right, and let's do one more problem. It says, suppose that 3x minus 2 is less than or equal to f of x less than or equal to x squared plus 1 for all x in the interval from 1 to 3. Find the limit as x approaches 2 of f of x and show your reasoning. So here, because this is always true for the interval between 1 and 3, and since 2 is part of that interval, that means we certainly can use this. We can certainly take this for granted in the context of taking the limit as x approaches to 2. So what I'm first going to do is take the limit of all the sides. So limit as x approaches 2 of 3x minus 2 must be less than or equal to the limit as x approaches 2 of f of x, which must be less than or equal to the limit as x approaches 2 of x squared plus 1. Then I'm going to plug in 2 for the left side and the right side to get 3 times 2 minus 2 less than or equal to the limit as x approaches 2 of f of x, which is less than or equal to 2 squared plus 1. Then we get 6 minus 2, which is 4. And then over here we get 2 squared, which is 4, plus 1 is 5. So we get that this limit must be between 4 and 5. And so in this case, we actually can't use squeeze theorem to directly find the limit. We know it's between 4 and 5, but we can't actually say what the limit of f of x would be, right? And they also didn't tell us what f of x actually is, and so we can't possibly find the limit in some other way. And so for this one, the answer is actually that it is not possible to determine. And the reason is because the limits didn't converge to the same value. In all our other examples, the limits converge to the same value. So we were really expecting for either both of these to be 5, both of them to be 4, or both of them to be some value. And in this case, they weren't. And so we actually can't determine exactly what f of x is, or what the limit as x approaches 2 of f of x is equal to, right? The best we can do is to determine that the limit is between 4 and 5. All right, well, as always, feel free to leave any questions you might have in the comment section, and we'll see you for the next one.